Information about the uncertainty of the wind and solar power forecast is very important when the penetration of such fluctuating renewable production is on the order of 10 to 20% or more. One example here is that the cost function related to bidding on various day-ahead and intraday markets might be asymmetrical. Here, forecast information about the uncertainty is crucial to obtain the full economical revenue. Multivariate full stochastic forecasts provide in addition also information about the persistence in time of the forecast errors. Full stochastic forecasts are often illustrated by drawing a set of forecast scenarios as illustrated. Wind and solar power generation and the related forecasting errors are not Gaussian, as explained in lesson 1. This also implies that it's not sufficient and not correct only to provide confidence bands based on the variance or standard deviations of the prediction errors. However, various transformation can help providing values which are approximately Gaussian and where the dependencies can be described by covariance matrices. Such examples are provided in the references. Since around year 2000, ensembles of meteorological forecasts have been used for providing probabilistic forecasts. The lesson learned, however, is that the meteorological ensembles must be corrected by a statistical model in order to obtain reliable prediction intervals. Furthermore, the mapping from MET forecast to output power forecast also contains phenomena which are tailored with uncertainty. Quantile regression gives a model for the quantiles. That is, a model, for instance, for the 90% percentile. Such techniques are very useful for providing probabilistic forecasts. The models can also explain how the variation of the uncertainty depends on various potential explanatory variables, like the wind direction, instability of the atmosphere, and the prediction horizon. Like for point predictions, the parameters of a model for a quantile have to be estimated adaptively. See the provided references. For probabilistic forecasts, the temporal dependency of the forecast errors is not described. However, by normalizing the errors, it's possible, as a first approximation, to describe temporal dependency using a covariance matrix again. For spatiotemporal forecasting, this can be generalized by using a set of auto and cross dependence matrices. Please again see the references. In recent years, it has been possible to use stochastic differential equations, so-called SDEs, to describe the auto and cross dependencies. SDEs have proven a powerful tool for wind and solar power forecasting. SDEs are able to provide simultaneous and robust description of the entire sequence of future wind power production. All information related to point, probabilistic, and time dependency can be represented and illustrated by forecast scenarios. Such scenarios are useful as input for optimization and decision making, and they can be used, for instance, directly in stochastic programming, which takes the uncertainty into account. It's very important to use a forecast provider which is able to generate joint probabilistic forecasts of wind and solar power generation and jointly with load. For probabilistic forecast, evaluations like the continuous rank probability score or CRPS has proven to be appropriate. Consequently, CRPS can be used for a comparison of various tools for probabilistic forecasting. However, in the case of full stochastic forecast, the CRPS is not fully adequate. In the reference list, we have provided new methods for forecast evaluations. Let me finalize by showing two examples on why it's so important to have information and reliable information about the uncertainty. Forecasts are crucial for being able to write bids to the power market. As a consequence of the forecast errors, a penalty is often used. In most situations, the penalty for providing a forecast that is too high is different from the penalty when providing a forecast that is too low. Consequently, the economical optimal forecast for bidding is most likely not the expected wind power production. Here, the optimal forecast is a biased forecast for minimizing the penalty. Please see the references for details. With more and more fluctuating renewable production, energy storages become more and more important. Storage are, however, often very expensive. In order to find the optimal sizing of the storage, and knowledge about the persistence in the forecast errors is very important. This figure shows that if the persistence is not adequately taken into account, then the sizing of the storage will be wrong and way lower than needed. The optimal sizing of the storage solution depends on the parameters describing the persistence. Again, please see the references for details.